We're going to cover a lot of ground in this lesson 8, day 1. I recommend that you have like a highlighter or something because later on in this section you're going to need to make some marks on your paper. But we're talking about the pieces or the components of a function, certainly when it's graphed. What are things we need to know about? And some of these you should already know because they are common to graphs, and graphing equations is a skill that I've seen you exercise. In this one, let's give this one a name. I want you to know that this is actually what we call a square root function. And I am going to do the entry task because the key features conversation is something that you need to know about. And I don't think we've listed them before this point. This is a square root function, and it looks something like this. This is, in fact, a negative square root function because it goes to the left. A positive square root function is the exact opposite and goes to the right. In this one of the things that you should know as a key feature is the y-intercept. So I'll make a list. Y-intercept. You need to be able to point to that as a key feature of the function. You also should be able to look at the other intercept or intercepts if they exist. So you might as well say and x as well. And that would be right here because on the x-axis, let's actually label. I notice there's no labels. I notice on the x-axis, the graph touches there. It's filled in. So we have an intercept that's on the x-axis. We don't have a straight line, so we can't really talk about slope. But if you had like a straight line, that'd be helpful. Maybe instead of talking slope, let's talk about increasing or decreasing. Like, is the function going up or down as the graph moves left to right? And if you see that, the graph is getting lower and lower and lower as we move to the right. So this is a decreasing function. Okay. We want to talk about something called symmetry, or like, can you fold it on itself and it perfectly matches? Like in B, it's symmetric, right? It's a symmetric graph because if you fold it on the y-axis, then you can get the graph to look exactly the same. There's a region where the graph is decreasing and a region where the graph is, or I should say the better word, there's an interval where the graph is decreasing and an interval where the graph is increasing. In this one, the function is decreasing from like negative infinity to 4. So we could write an inequality notation. The negative infinity is less than x is less than or equal to 4. So anything from negative 4 and smaller is a place where the graph is on a decreasing direction. For part B, the graph, the interval where it is increasing would be from 0 to infinity. So 0 is less than x is less than infinity. Notice that I switched from using the equal to sign to 0 because I don't know what's actually happening right here. After all, it's a y-intercept. And this is a function. This is an absolute value function. So we need to know some names. In an absolute value function, we actually have 2 x-intercepts. Usually, likely, it's possible. Not always, and maybe you can think about when it's possible to have only 1 x-intercept or when it's possible to have none. But the point is that typically we should be looking for 2 x-intercepts with an absolute value function. We're not really going to talk about square roots and absolute values more, but I just want to make sure you knew about them. C and D, extra practice. Extra practice. And in terms of the list of key features, we're going to add to it, but so far I just want to get you keyed in on the idea of key features are intercepts. So that's, both x and y intercepts. Where is the function decreasing or increasing? Is the function symmetric? And we'll run across some more. So maybe give yourself some space to run a couple extra dots. Oh, I'm sorry. Here you go. You can see it all. There it is. Okay, turn the page. Page 20. On page 20, we got some fill in the blanks. So you can either skip ahead after I write them all down, or you can listen to me talk about them. But here you go. So function is a special relationship where each input has a unique or unitarily unitarily bound output. As in there's only one output bound to that input. Dang, this is the best term math-wise. I'm going to star that. This is totally a Labrantism. All right, so if you quote it, you got to give me credit. Each input has a unitarily bound output. Really what I mean is if x equals 1, then f of x has only one output possible, right? I can't put another number here. I like that better than unique. I really just stumbled upon that. I'm kind of geeking out about that. Okay, it's often written as f of x, and that's because x is the input value. Right? The domain of a function, here's a key word. If you want to highlight it, you can, but it is already underlined. The domain of a function is a set of all of the values that go into a function. It's usually known as the input value or the x value of a function. The range of a function is the set of all, you guess it, outputs. You know what? The dependent variable, it's the f of x value of a function. It's called dependent because the value f of x depends on what you put into the function. So it usually goes input. That's the number you pick. The function works on it, chugga, 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 spit, and out comes output, f of x. And here are two more key features. So I'm going to flip to the first page, making my list, domain and range. Maybe that's the same line, maybe it's two separate lines. We should be thinking about the domain and range, the list of all inputs and outputs. Okay, example 2. Example 2 is setting up for this idea of domain and range and looking at x values and looking at y values. This isn't even homework. This is just straight up extra practice. Although I am curious, what's the ordered pair for D? What's the ordered pair for F? Okay. I'm sorry, page 21. And so on page 21, we have a little bit of an element of review in the fact that we have a set of ordered pairs, another set of ordered pairs, this for this and this for this. But if we look at is the relationship a function, we got to look at all of the x values. If the x values ever repeat, we have to look at their y values. And so no, this is not a function because 0 goes to 0 one time, and then 0 goes to -18, so that makes it not. We could say it doesn't pass the vertical line test because at 0 there are 2 y values. But we can't put the domain in ascending order. Uh-oh, I gotta think about the smallest. Ascending means from smallest to biggest. So the domain is all of the x's such that we are looking at -3. I'm going to cross that. And then 0 and 2 and 7. And we'll put some little curly Q braces around it. This is notation for high-level math. You guys are on your way to that level. So when we say like this symbol notation, it's all of the x's such that these are those x's. And the braces lock it all down. The range in ascending order, so curly Q braces, f of x, because range is f of x. Now we're looking at all of the y values. So y, because -18 is the smallest. And then next up is -1. And then next up is 0. And then next up is 9. Yep. So we have our range in ascending order. And I'm just trying to make sure that I want you to disassociate this number goes with this number. It's not that. It's not this number goes with this number and this one. It's actually about the collection. It's the collection of all of them. There are 4 numbers that make up the domain. And coincidentally, there are 4 numbers that make up the range. There doesn't have to be. Homework. Let's take a look at example 4 then. So in example 4, domain is x's. So we have the x-axis labeled. And range is the y values, or f of x values. And so really all that we're looking for is, let's say I'm going to use my color now, is that the domain would be any x value that the graph matches. So that would be this x value, or and this one, 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 and this one. Making a list, that's the x value -4. So the domain. It's the set of all x's such that we're looking at -4, -3, -2, -1, 0, 1, 2, 3, and 4. Range is up and down. So the range would be, well, this point, its range is all the y values. So this y value, and 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 this y value. And oh, these are the same y values. Ha! Okay, so because we have a y value and a y value and a y value, and then it repeats, that's fine. This will be a smaller list for the range. The set of all y values, that's range, such that we're looking at -2, -1, 0, 1, and 2. There's your range. It is the collection of all x's for domain and the collection of all y values for range. This actually helps us see the range, the domain and range when the graph is a smooth, continuous curve. Remember what I did with the domain. I picked a location and I found its x. I picked a location and found its x. I picked a location and found its x. And so by picking all these locations, I'm seeing that there is, well, I mean, gosh, I could go in this direction to -infinity. So from -infinity, and then I can go this way to the right for forever to +infinity. I guess my domain would be the set of all x's between negative and positive infinity. But it's not true for the range. Domain, blue for range. So if I pick a location on the graph, like right here, I can go to the y-axis. Range is y-axis. I can pick here and 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 here. Oh, even over here, there. But you know what? I'm not picking some y values. None of these y values have any graph next to them going side to side. And you know what? I'm going to put a word here. This is called an exponential. And so I wanted let you in on some knowledge about exponential functions. Exponential functions are completely, entirely positive or negative, but they never actually hit zero. This gap always exists between the line and the x-axis. So I guess technically the range will be the set of all y values such that we are bigger than 0, because side to side we're hitting positive numbers. And you could even say less than infinity, but this part's not even really necessary. Okay, there you have it. From a graph, you can look at going at an x value, or from the point down to the x-axis to talk about the domain, or from a point to the y-axis to talk about the range. And in this area, there is no range. And in this area, there is no range. And so we don't want to mention those in the description of range. I guess that continues. Let's take a look at page 22. That continues with a table of values. In a table or in a relationship, an ordered pair list, homework, that you look at all of the x's, because all of those x's are part of the domain, and you look at all of your y values because those y values are part of the range. All right. Let's see. B's good, but I'm going to call it extra practice. C's definitely homework. You need to do this one. C. Remember, for letter C, pick a point on the graph, go to the x-axis. Pick a point on the graph, go to the x-axis. Pick a point, pick a point, pick a point. And because of the arrow, there is only one spot where the graph stops, and there are no x's past that. So from right here, the graph doesn't exist. There is no domain greater than that number. Same is true, although it's kind of hard to see based on the graph, so I hope the numbers are there to help. But pick a spot on the graph, go to the y-axis, go to the y-axis, go to the y-axis, go to the y-axis, go to the y-axis. All of these spots, when you go to the y-axis, you start to realize that there is a maximum value. And there's nothing higher than that value. So the domain and range are restricted. This curve, don't worry. This one, it might have a name, but I'm not going to teach it to you now. Maybe in Algebra 2. All right, that's page 22. Looking at what we have to do, we still have some left. Here we go. A ball is kicked from the ground with an initial velocity of 40 feet per second. Consider the graph below. 40 feet per second. Hang on a second. Let me do a little quick calculation here. 40 feet per second is approximately, Google says 40 feet per second is 27 miles per hour. You know, I was all ready to be impressed. And then I thought, like, my grandma can throw faster than that. Okay, so select all of the statements that correctly describe the domain or range of the function. Well, in order to find domain, I guess, wait a minute, this doesn't make sense. That would be below the ground. How can you have kicked from, this part of the graph shouldn't exist. And you know what, this part shouldn't exist. The ball didn't, like, fly up in the air and then start burrowing into the ground. So this part doesn't exist either. I think that really just limits us to the domain of the function is a set of, it's not necessarily rationals. Rationals allow for gaps. It's this one. I'm going to check B. Real numbers. This is a continuous curve. Rational is not continuous. There is a gap between a half and, which is 4/8, and 5/8. And so because there's a gap there, you can't quantumly jump from one to the other. You have to continuumly travel. If you don't know what that means, don't worry about it. The range of a function is a set of integers between, nope, not integers. Once again, we're not talking about skipping from, oh, hold on a second. Domain. Pick an x, pick a spot, go to x, pick a spot, go to x, pick a spot, go to x. So as you go to the x-axis, you're pointing out domain values. So like, I could pick anywhere along these. I just need some example values from 0 through 0.5, through 1, through 1.5, through 2, through 2.5. So here we go. We have from 0 to 2.5. That's the range, the domain, my bad, the domain. Pick a spot on the x-axis. No, pick a spot on the function. Go to the y-axis. Horizontally as you can. Right? We hit it like a max. And these points all right here, they actually show us that the range is y, range goes from 0 to 25. Range is the set of real numbers between 0 and 25. You know what? You should graph this. This is a square root function. I wonder why. And I'm going to recommend that your graph actually goes along, let's see here, yeah, right here, right here. Maybe use these lines. Yeah, I'm using a yardstick, but I'm thinking about the graph that's right here, and I'm thinking that you should put some lines along this right there. And then let's label some scales. So I'm going to say skip 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. So when we say x minus 2, you'll notice that this graph looks particular, but after you graph it, do the same, check your domain values. Check your domain values, and maybe you're getting a hint that because of the way that I drew this, label 1, 2, 3, and scale. So there's my scale, there's my labels. Okay. As you graph this function from Desmos, you'll start to notice that you can think about the color of pick a spot on the function and go down to find a domain element. Pick a spot of the function and go to the y-axis to find a range element. And when you've done that multiple times and you kind of found like the upper limit, or you've kind of found the starting point and the ending point if they exist, you can start thinking about restricting the domain or range and then writing something like this to describe them. Flipping to 24, 24 is the closing. You should absolutely do the closing. The success criteria and the exit ticket, you should absolutely do those. And of course, the problem set is homework.